Hey y'all, in this video we will be focusing on how to solve question 35 from the first exam. So, this question is asking for the number of sp, sp2, and sp3 hybridized carbon atoms in the molecule of Viagra. If you recall, we learned about VSPER theory, and under this topic we used steric number to determine the geometry of a central atom. To find steric number, we need to look for and count the number of electron environments. This includes lone pairs of electrons and sigma bonds only. Once we have those numbers, we can add them together to get our steric number. This steric number will give us the hybridizations for each carbon. We covered hybridization in class before discussing this topic, and so it will be mentioned as I explain steric number. A carbon forms a maximum of 4 bonds. If we count 4 single bonds, that will give us 4 sigma bonds, hence a steric number of 4. The carbon will have to accommodate for 4 orbitals, and to do so it must be s1p3 hybridized. Why? Let's take CH4 for example. Recall the electron configuration of carbon. It can't satisfactorily describe methane's bonding nature because it shows only 2 atomic orbitals capable of forming bonds. We know a carbon forms 4 bonds, not 2. We can solve this by imagining an excited state of carbon. A 2s electron promotes to a 2p orbital. Now we have 4 orbitals for bonding. But the tetrahedral shape of methane has not been accounted for. To explain this, Pauling suggested that this carbon's electron configuration does not necessarily have to be the same as that of a free carbon. Instead, he averaged or hybridized these orbitals, giving us 4 degenerate s1p3 hybridized orbitals. Thus a carbon's steric number of 4 will indicate 4 single bonds and a hybridization of sp3. Moving on to double bonded carbons and sp2 hybridization. Let's look at ethylene, which has a planar geometry. Each carbon atom only needs to form bonds of 3, not 4. Therefore, only 3 hybridized orbitals are needed, 1 s orbital and 2 of the 3 p orbitals, with the 4th p orbital remaining unaffected. The result is a C atom with 1 p orbital and 3 s1p2 hybridized orbitals. For clarity, only the front lobes of the sp2 orbitals are drawn. The p orbital is the red head, blue tail region, and the gray are the 3 sp2 orbitals capable of forming sigma bonds. One between the carbons and the rest for the neighboring hydrogen atoms. The pi bond is created with the overlap of the remaining p orbitals. Therefore, the sigma bond overlap between the 2 carbons and the pi overlap between them makes the double bond. Since a double bond contains a sigma bond from one of the sp2 orbitals, count the double bond with a numerical value of 1 for steric number, and then add the 2 other sigma bonds. This gives our steric number of 3 for the carbon we are focusing on. Each carbon will be sp2 hybridized. And finally, sp hybridization and triple bonded carbons. Take a look at acetylene. A triple bond is formed by sp hybridized carbon atoms. 1 s orbital is averaged with only 1 p orbital. This leaves 2 p orbitals unaffected. As a result, there are 2 sp orbitals and 2 p orbitals. The 2 sp orbitals are available to form sigma bonds, 1 on either side of each carbon. And the 2 p orbitals are available to form pi bonds. Thus, a triple bond forms between the 2 carbon atoms due to the overlap of sp orbitals in between them and the 2 unaffected pi orbitals. If you focus on 1 carbon, count the sigma bonds and you'll get a steric number of 2. Now that we reviewed hybridization and steric number, let's look at the question again. Clearly we are looking at a bond line structure. Be careful as CH bonds are ignored, but that doesn't mean that the hydrogens are not there. It's simply clearer and faster to draw it this way. The carbons are represented by corners or ends of bonds. If we start on the left side of the molecule, imagine the hydrogens drawn. You can draw them yourself, but being able to visualize this is key. I will draw the undrawn hydrogens for this carbon here. It already has 1 bond to nitrogen, so we need 3 more bonds since carbon forms 4 bonds. This gives us 4 sigma bonds, so we know this carbon is sp3 hybridized. Now let's continue this for the ring here. Imagine the missing hydrogens. Each of these carbons will then have 4 bonds and be sp3 hybridized. Ignoring the heteroatoms, let's continue to the other ring. All of these carbons have double bonds, and as mentioned before, they will be sp2 hybridized. And now going up from here heading towards the other rings, we get more sp2 carbons. Be careful as it's easy to forget these carbons in the corners and underneath the oxygen, but we got M. Next, let's finish up these remaining carbon atoms. They all seem to be sp3 hybridized. So for our last step, count the number of sp3, sp2, and sp carbons. Start with sp3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have a total of 11 sp3 carbons. Now time for the sp2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 sp2 carbons. And it looks like we have 0 sp carbons. We would have needed a triple bonded carbon for this. So, I hope this helps some of you out. I know chemistry is difficult and we all have our strengths and weaknesses in certain areas, but as we put in the effort, we will make this journey together, and I truly wish you all good luck.